Okay, welcome to the lecture 3 of vibration, which is force vibration. So for the first case, let me show the undamped vibration. So um, okay, let me review the equation of motion of vibration. Actually, it's in the form of second order differential equation like this. So mass represent the mass of the object. C is the damper, damping coefficient, and K is the stiffness of the spring. F is the external force applied on the object. Okay. So for force vibration, the input to the system is in the form of trigonometric function. For example, here is cosine omega t, where omega is the frequency of the input force, and the amplitude of the force is f0. So actually the system itself can have a sort of vibration, but then you impose the input or the external force uh, in the form of trigonometric function, which is to vibrate it as well. Okay, then we'll we will observe the behavior or the motion of the object. Okay, so this is the illustration of the solution or the motion of the object, because the equation is linear. Yeah, here is linear. You have homogeneous solution which uh, die out after a certain period of time, which means the longer the time is, the effect from the homogeneous solution disappear. And the particular solution, of course, it uh, depend on the external force applied on the system, or you can call it input for the system. Okay, then the combination of the two solution is like this. You have homogeneous that has transient part, and you have particular solution that is steady like this. So when you combine these two together, you have transient, but somehow the transient has unorganized, or how say, um, a not recognizable pattern of oscillation, right? But after then, the homogeneous part die out. Then what remains is the same as the particular solution, right? Yeah, that's why I usually say the steady state actually is the particular solution. Yeah, first let's see the undamped system under harmonic force. Undamped system means you take out the damper. So in the equation, the term CH dot disappear. Now you only have these two terms for the left-hand side. Um, then the solution, the homogeneous solution, looks like this. Why? Because when you look at the characteristic equation, it's m lambda square plus k lambda, plus k equal to 0. So lambda equal to plus minus j square root of k over m. So it is pure complex number. Then you can have a pure trigonometric function. you don't have the exponential term, right? The exponential terms come from the real part of the characteristic root. All right, and square root of k over m is denoted by natural frequency omega n. Okay, you can see here natural frequency. You call it natural frequency. I mean, even though if you don't have external force, let's say if you, in the case you don't have external force, and you start the initial conditions somewhere, and then you let it move freely, it will oscillate at the natural frequency omega n. Okay? Natural means no external force that force it to change or to vibrate in a certain way. So it vibrated by its own nature. So and then particular solution, of course, the system must vibrate according to the external force. It means if you input the external force with the frequency omega, the system would vibrate at the frequency omega. This is what particular solution means. But you just you are not certain what amplitude would be. Okay, so then let's assume particular solution is one variable amplitude times cosine omega t. Okay, omega here is same as omega of the external force. Then to find x, capital H, you need to take the second time derivative and substitute in here. Okay, so let me do it. I take the time derivative here first. So h, you can write here h dot p equal to minus h omega sine omega t. Minus sign, right? And then h double dot p equal to minus h omega square cosine of omega t. Let's substitute into this or the original equation. You can have h double dot means minus h omega square cosine omega t minus k h omega sine omega t equal to sorry, I think I make a mistake. I make a mistake. M times h double dot, this one, minus h omega square cosine omega t plus k times this one. Okay, so h cosine omega t equal to f0 cosine omega t. Equal to f0 cosine omega t. So from here we can find h, right? I can have minus m omega square plus k h equal to f0. Yeah, so here k minus m omega square. Yeah, so this is correct. And then just normalize the denominator, which means just divided by k So here divided by k, and here divided by k. So F divided by spring constant would be some displacement, right? That's why this is denoted by a displacement. And so here you can have, because omega n is k square root of k over m, so you can rewrite this term as omega divided by omega n or square, right? Now it's very interesting. Why I say interesting? Here you will see. Then the complete solution here, and don't forget this term is just this term, okay? Yeah, using initial condition, h0 equals some value h0, h dot at 0 equals to some value, yeah, initial velocity. Then you can have C1 and C2. Final solution looks like this. Okay, here is C1. Here is C1. Yeah, this is C1. This is C2. Yeah. Okay. Now, something that you need to observe, which is the amplitude, the maximum amplitude of H. Yeah, maximum amplitude of H. Yeah. So look at this form, the formulation. You can see that this ratio, actually H is amplitude, and this one is just some displacement. The most important thing is the right hand side. You can see that when omega is close to omega n, it means, you imagine you have a pendulum that can oscillate at a natural frequency, but when the force pulls it at the same frequency, it's like you have a kid in a swing. If you want to swing, go further and further, you must push the force at the same frequency, right? It go there, come back, and then you push it the same frequency. Like that, then the swing can go higher and higher, right? So here is it's similar. You have a vibrating system, and the external force excited on the system uh, with the frequency the same as natural frequency, then the vibration will go higher and higher. I mean, the amplitude of the vibration higher and higher. Okay. This phenomenon is called resonance. So yeah, so resonance is not a desired phenomenon. For example, you want to bring a satellite by a rocket. Let's say you design a satellite that have of course it has a certain natural frequency. If the frequency of the vibration from the rocket is the same as natural frequency of the satellite in the rocket, maybe your satellite is broken before it is released from the rocket. See? So this is very how to say, very cautious phenomenon. You need to investigate uh, your product, or when you design, when the product has a certain excitation force. I mean, the excitation, the force that has cycle. Um, Yeah, let's observe case 1 when the ratio of omega and omega n is less than 1, then the response form of particular solution is unchanged. And the harmonic response of the system HP is said to be in the phase with external force. It has the same phase of external force like this. So when F0 is maximum, the amplitude is also maximum. Okay. But in the case 2, when the frequency of the excitation force is higher than the natural frequency, then the amplitude of particular solution is negative. Then the phase of the excitation force or external force is 180 degree out of phase from the phase the phase of the particular solution is 100 degree out of phase from the external force. So it means when the external force is maximum, then the amplitude h of the particular solution is minimum like this. Okay. Our 180 degree out of phase look like this. Any question up to this point? Okay, just remind you the particular solution. Here. And this part can be rewritten like this. So that's why you just compare omega and omega and omega over omega n. Okay. Case number 3, omega over omega n equal to 1. Yeah, this is what I already explained. The amplitude become infinite, which means that omega, the forcing frequency is the same as natural frequency, then resonance happen. And the total response of the system is rewritten to be this. Okay. So actually from here you can take the limit. Okay, take the limit omega approach to omega n. So finally you can have the final solution to be this one. And if you plot this, if you plot this curve, you can see that the amplitude of the oscillation grow over time. Okay. So here is the summary of the solution for the 3 cases. Okay. Yeah. Okay. So you can catch up the phenomenon of this kind of vibration. Everything can be explained by the mathematical expressions actually. I mean everything about vibration. Okay, if you don't have any question, then I can go to the next point, which is damped system under harmonic force. Uh, yeah, for this system, we include this term. I mean, C is not zero. And yeah, similarly, the way we find particular solution, um, we choose HP is certain amplitude times cosine omega t, but with some lack of phase phi. Okay, and then the next process is to find capital H. So how you can find capital H? I just give you a step-by-step process. So first you find H, yeah, you have H equal to H cosine omega t minus phi, and then you find H dot P equal to H cosine, no, minus H omega sine omega t minus phi, and then HP double dot equal to minus H omega square cosine omega t minus phi. And then you substitute this 3 into this equation, then you can find capital H. And you can also find phi at the same time. Okay. And again, we can denote natural frequency is the square root of k over m. Okay, always. And damping ratio zeta. Yeah, I can review it a little bit. So, what is zeta? Yeah, actually just compare this one with h double dot plus 2 zeta omega n h dot and plus omega n square times x. So you compare these two. This one you can rewrite this c over m, and this one k over m. Yeah, compare these two, you can find zeta actually is just the ratio between c and square root of mk multiplied by 2, and that's why it's called damping ratio. Okay, and this one is called a static deflection. Yeah, under the static force F0, if you put you you give the external force F0 without this one, just F0, then you get the displacement, static displacement delta st. Actually, when you solve particular solution with this one, for this one, you can get the HP particular that actually this one at our ST just equal to F0 over K. That's why it's called static deflection. And R is the ratio between the frequency of the external force and the natural frequency of the system. Okay. Do you follow this? Okay. Yeah. So follow the process I just showed you earlier. You will find the ratio between the amplitude in the case of, I can say, forced vibration and free vibration. This one like you just put the force constant, but this one you put the force with frequency. Okay, and you want to find the ratio between these two cases. It's like that. So the right hand side here, you see the zeta, which is damping ratio, and R is the ratio between frequency of external force and the natural frequency of the system. Also the phase, the lag phase between particular solution and the external force. Okay. Yeah, so this phi also in function of damping ratio and frequency ratio. Yeah, so here is the vector representation. Let's say I of t, or let's say this is t, and this is the magnitude. So I of t represented by a rotating vector. So the magnitude of f, I mean on this axis, would be oscillation like this. Okay, oscillate like this. And then the amplitude of not only just amplitude, but the particular solution itself is also rotating vector, but it's out of phase from f of t by minus phi. Okay, and it of course rotate at the same frequency, looks like this. Okay, the dashed line here. So out of phase by phi and with a certain amplitude, which is this. So the amplitude of this one is this time, yeah, time this one. Then you can plot by choosing the parameter damping ratio for different curve. So you can plot the amplitude ratio versus the frequency ratio R here. Okay. And now you can observe here, if the frequency ratio is smaller than 1, okay, less than 1, then the curve is below 1. So I mean um, the amplitude of the oscillation becomes small. Okay. And with the smaller damping ratio, no, sorry, higher damping ratio, because when high damping ratio, it means um, the system is not moving fast, because higher damping ratio means the damper is very strong. So if the H04 is very at the low frequency, it does not disturb it so much. It does not vibrate so much. Okay, you just try to visualize this and get the insight of this craft explanation. And when the frequency ratio is larger than 1, okay, uh, at the large damping ratio, okay, the curve is still the lower, okay. But when if damping ratio is small, which means the damper is not so strong, so the system is like you have mass and spring. It approaches to undamped system. So that's why when you see the damping ratio smaller than 1 and becomes smaller, then you can see the curve is go higher and higher. Okay? Now let's observe if the frequency ratio is 1, the resonant phenomenon. Uh, let's see whether the amplitude can go to infinity or not. Look at here. If frequency ratio is 1, this is 1, this is 1, but this term becomes 0. But this term is not 0 as long as zeta is not 0. Okay, so it means what? It means as long as you have damping ratio, the amplitude cannot go to infinity. Okay, this is what it means. So here let's summarize. For the undamped system, which means this one equal to 0. So actually this equation explains both cases. If zeta is 0, when frequency ratio approaches to 1, then the magnitude or the magnitude ratio go to infinity. And with any amount of damping ratio, any amount of damping ratio reduce the magnification factor for all value of forcing frequency. Okay, so this is just repeat what I just explained earlier. As long as you have small damper, then this ratio cannot approach to infinity. So for any specified value of frequency ratio, a higher value of damping reduce the value of is this ratio. How about in the case of degenerate case of constant force? Constant force means there's no frequency omega. Okay, or we can say omega is 0, so the damping ratio frequency ratio is 0. Then I'm just approach to 1. I'm just equal to 1. Maybe we are not taking the limit, but we set r equal to 0 directly. Then is just 1. All right. So this equation explains all the cases. And the last case, this card. the reduction in M in the presence of damping is very significant at or near resonance. Yeah, so as you can see, uh, from for damping ratio from 0.1 to 0.3, you can see a significant reduction of M, right? But then when damping ratio go higher, like from 2 to 3, the reduction is not very significant. Okay, not so much here. The reduction here not so much. Here not so much, but here the reduction is a lot. And number 6, the amplitude of force vibration become smaller with increasing value of forcing frequency. So small increasing value of forcing frequency means R is larger here. When R is large, you can see this part R become large, then the magnification factor becomes small. So if the frequency of the external force is very high, then the system just filter out, okay? Filter out high frequency because the system is low pass filter. Okay. Number 7, for damping ratio between 0 and 1 over square root of 2, maximum value of occur when R equal to this. Okay. So you can see here, for this curve, the maximum value is 1, but for this family of curve, okay, this family of curve, actually maximum value of okay, maximum value of can be expressed by this, okay, R equal to this. And the maximum value of amplitude when R equal to start value can be computed by this formulation. Okay. So in summary, from this one equation, you can make a graph, a family of graph with the parameter of damping ratio. Then you can make a summary with 8 points, okay, from 1, 2, 3 until 8, like this. So I think for 1 degree of freedom vibration, if you understand all these 8 points, it means you have the insight of the vibration itself. Okay, you can feel how the behavior of vibration, okay, with different cases. Yeah, this is very good summary. Maybe if you are not a fan of mathematics, maybe you can go strictly to the graph and learn from the graph. Okay, try to get the insight. And especially try to connect with the actual phenomenon. Try to feel the, like a damper. What is damper? How you can feel the damper? Something that when you want it to move fast, you need to pose a very strong force, for example, something like that. Because you can see that when we talk about vibration, we can see damping ratio appear again and again, and also frequency ratio appears again and again. Yeah. Any question? Yeah. What? Oh, small delta. Oh, yeah. Small delta is a particular solution when you apply the force only just F0, constant. If you apply external force F0 to the system, uh, why I say this here. So this is the system, and you apply the F. Yeah. If you apply F, it's just a constant. You pull it, so it will display at a certain point and then it stay there, right? So that displacement is called delta. Yeah, denoted by delta. And how can you find it? In that case, the right hand side is constant, then the particular solution is a constant, right? If particular solution is constant, so the derivative is 0, second derivative is 0, which means kh equal to that constant, or yeah, it's actually f kh equal to f0, then the constant, yeah, the constant h c must be equal to f0 over k. And actually we denoted this as a delta st, right? Static. Yeah. So the meaning of here, the ratio here, means that the amplitude of the vibration in the case of dynamic force means oscillate force, with the ratio of amplitude in the dynamic case and the amplitude of the static case. It's like that. So static case, the displacement only like that, only one time and stay there. But in the dynamic case, it oscillates like this, and we take the amplitude and make a ratio with this static case. This is the meaning of Any more question? Sumlan? You look very curious. Kumlai? Any question? No. Okay, then I will end our lecture now.